So I'll carry on. We were just talking about the cultural dating as a form of relative dating, but there's also absolute dating. So relative dating dates things relative to one another. Was it earlier or later? But we don't actually have an exact moment in time in the past that we can put on a calendar. So it could be relative dating could be 1 million years, 2 million years, 3 million years, 10 million years, 100 million years apart from one another. But how do we know that it's not 10,000 years or 1,000 years or 50 years? Well, thankfully we have some scientific means to actually test the dates of things absolutely. And this is the difference between absolute dating and relative dating. So absolute methods of dating, one of which is on slide 22, is what's called dendrochronology. Dendrochronology is the principle that you probably are aware of already, that there are tree rings, that annual plants like trees, they form new bark every year. They go dormant in the winter and then they grow in the summer, and they add a ring to their trees, or to their trunk. And if you can access that sequence, you can actually have a year by year by year sequence. And environmental changes take place, and that shows up in the tree rings. And you can overlap those, that if there was a fire that took place, one tree that's a little bit younger can overlap with one that was a little bit older and maybe died in the fire. And so you can actually build up a sequence going back and back and back. Some trees that are alive, the Colorado bristlecone pine, some of them are over 2,000 years old. So that gives us actually a pretty deep sequence, and we've now done dendrochronological records going back to about 10,000 years ago. This also gives us a calibration for some other methods like radiocarbon dating that is on slide 23 that helps us to give more precision to the another method of radiometric measurement. Now, what I mean by radiometric is that there are certain elements, all elements, have different forms, and they're called isotopes. Some are stable, which means they don't change, they're just fixed, and others have a different number of neutrons in them, and it's an unstable amount. They're either looking to add neutrons or they're looking to get rid of neutrons. And those ones that are looking to shed neutrons will transform into some other element. In this case, what we're going to talk about is carbon-14 dating. An unstable isotope of carbon, which all living things are carbon-based because they're very easy to join to other elements to make things like amino acids and proteins. Carbon is very good for that. And here on Earth, we are carbon-based life forms. And an unstable isotope of carbon is carbon-14. And your body maintains a particular level of carbon-14 while you're alive. Every living thing's body, plants, animals, everything, fungus, maintain a certain level of the isotope carbon-14 in your bodies. But once your body, or any living thing's body, stops living, it's no longer keeping that level of carbon-14 in your body, so at a certain level. And that's where radioactive decay starts to take place. That isotope that's unstable, your body's been maintaining that level of unstable isotope. It's perfectly harmless. It's necessary for your life. But once your body stops doing that process, the isotope of carbon will start to break down, will start to decay into something that is stable, and that is nitrogen 14. So carbon-14 transforms into nitrogen-14 at the moment of death. Now that is something that a physicist named Willard Libby in 1955, published the first paper. In 1949, he discovered this, that this decay isn't just sort of at a random pace, it's a fixed rate. So once a living thing stops living, it stops maintaining that carbon-14, and that radioactive decay starts to happen, and that is at a fixed rate. It's like a clock starting from the moment death occurs. And if you can measure how much carbon-14 has transformed into nitrogen-14, you can, that ratio, that proportion will tell you how long ago that thing died. So a tree, or a bone, or a seed, or a plant of some sort. Anything that was once alive, and you have the carbon-14 that you can measure, you can actually date absolutely something from the past. But you've got to have that carbon. So a stone was never alive, which means that it never died, which means that there's no carbon-14. So a rock carving out at Red Rock or Valley of Fire, those rock carvings have no organic elements to them. You cannot date them. That's not possible. But if there were human remains that were in front of that were of the people that carved that, you would be able to tell when that human died. So how old that carving was done by that particular person. If that was the person, if you could assume that that was the person who did it, which you not necessarily can. Now, this is one of the first methods of radiometric measuring. You've probably heard of carbon-14 dating or C14 dating or or carbon dating or one of these terms. It was the first of these that was used. We have other methods now, and I'll come to those in a moment. Slide 23 has the sort of life cycle process of what happens to carbon in the atmosphere and how it gets into bones. But the ratio of carbon-14 to nitrogen-14, although it takes place at a fixed rate, eventually it's going to run out of carbon-14. You only have a certain amount in your body, and that rate it's a clock ticking, but eventually that clock's going to run out of time. And once it gets to half of the amount that it's decayed into, that's called a half-life. And for carbon-14, its half-life of radioactivity is 5,730 years, which means that half of that is now gone. Now, it's a little bit like Zeno's paradox here, because the next half-life is half of that, which is also 5,730 years old as well. And so this the second half-life is also 5,730, and then 5,730 and 5,730. And but eventually it will be so little carbon-14 that it will be unmeasurable. And so this ratio will be so overwhelmingly nitrogen-14 that the clock is essentially out of time. Now, we've been able to date things up to about 75, 80,000 years old, but after 50,000 years, it's unreliable, or it becomes more problematic. So the more recent it is, the more reliable our dates are. Well, that's not entirely true, but after 50,000 years, they become more reliable, but prior to that, they're pretty consistent. But they give us a date range. They're not actually a calendar date. They are before present. BP is the term we use, which because Willard Libby published this first paper in 1955, we had to decide what present was. Before present is 1950. So unfortunately, we didn't wait till 2000 to do this. It would have been a lot easier. So every BP date that you give is actually before 1950 is the date that we use. And you can convert that into a calendar year using Gregorian calendar or Kurdish calendar, whatever you want to use. But it's before 1950 is what science is measuring it by in this method. And it will give you a plus or a minus. It will be an error message, an error reading, that it will be plus or minus 10 years or plus or minus 20 years. And it's equally likely to be any date within that range. It's not that if it's 2,000 years old plus or minus 20 years, that it's more likely to be 2,000 years rather than 2,020 years old. It's equally either 1980 years old or 2020 years old. And anywhere in between is equally likely. But that's still an absolute date. It has to be that old. Even if it's not a precise calendar date, within that 40-year date range, we know that that living thing must have died. So if we want to date things earlier, if we want to go back earlier in time, and that's going to be important for primate evolution and hominin evolution, so for our story, we need to go back farther than just 50,000 years ago. Well, there's other methods of dating that aren't just relative but absolute. And so things like other radiometric isotopes. So argon, argon decays into potassium, and that half-life is 1.3 billion years old. And so we're not talking about 57, 30 years old. It's billions of years old. So we can go back very far in time, but it's not when the date of something was living. That's the problem. It's only dating the minerals in the stratum from which a fossil comes. So we're dating the soil around a fossil, not the fossil itself. So also there's argon potassium and radiopotassium dating. And this is actually the slide number 24 actually has a whole list of different dating methods. Carbon, uranium, potassium, argon, and another form of uranium are methods of dating past things. Another method of absolute dating is that the Earth's magnetic pole shifts periodically on the Earth, and it magnetizes rocks. And so if you find rocks that are magnetized in a particular stratum, and it is polarized into either the south or the north, that will tell you at least that it is consistent with a particular time period.